Welcome to another Out of the Office. This is Bill SCHUh, and we're taking a little bit different tack today than we've had on previous Out of the Office episodes. Here we'll be actually doing a MIL Standard 1553 training. We've got some customers on the line. They'll be asking some questions possibly, and I think that it will be a good opportunity for those of you who are not let's say, experts in 1553, or if you just need a refresher on 1553, this is like the introduction to it. There's no real deep understanding that will be presented here on further application, but a good introduction to the standard. I think you'll enjoy it. Here we go. Okay, so that we're all very clear, this is being recorded. And we'll post it. Bill and I do a YouTube, if you will, channel called Out of the Office, and so we'll put it up there and send out the link for people to gain access to it. And we do other videos that we have up there on how to use different products, so you'll be able to see more. All right then. Okay, so we're here. What is MIL Standard 1553? All right, in the true sense of the word, it's just a document number. You know, and so it's nothing mystical. There isn't any particular way, like on a 727, how they came up with the name based upon angles of the wings and all that kind of stuff. It's just a document number. And what it specifies is a local area network that travels at a blazing 1 megabits per second. That's not bytes, it is bits. And so your effective throughput is somewhere around 800 kilobits. Now, the thing that makes it still viable today is that it's command control. It's very fast in response time, being in that 4 microsecond response times, and it's high voltage signal as compared to doing Ethernet or even some of the other networks. And so it makes it a really good, strong characteristic for command control, and especially if you're looking at things that need to be controlled, like in the 80 hertz or less. Ideally, it can go higher, but that's usually in the 40 to 80 hertz is where it gets its most applications. Today, the biggest part of the applications are satellites and weapon systems, radio controls, and of course, weapons, as I said. And there's a few other things that are controlled by it. A lot of times they'll do the control with 1553, and then they'll use Ethernet or Firewire or Fiber Channel or something else to get a bigger pipe of data through. So 1553 will support 31 computer systems on it. There are remote terminals, there are bus controllers, you can even put monitors on it. And it's a drop bus, and we'll see what that means in just a minute. There's not many drop buses around anymore, simply because most of the newer networks are controlled through switches. And so this kind of is one of the few robust networks that has no electronics outside of the LRU, active electronics, I should say. All traffic is managed, as I said, as the command response by the master, which is the bus controller. So just to be clear, nothing happens on 1553 unless the bus controller tells it to happen. And so that's kind of clear. Basically, it's a twisted shielded pair transmission media. And so I just threw this wire up here as an example of, hey, that's what it looks like underneath the blue cables if you have them around your lab. And that's about it. I mean, it comes in different kinds of wire you'll see for the aircraft, spacecraft. It'll look different, but in essence, that's what you're dealing with. Any questions? All right, some basic terminology that I've already touched on. The bus controller is a terminal that is assigned the task of initiating all information. Bus controller, like the rest of 1553, are software controlled. They're really basically The bus controller, the remote terminal, the monitor are part of the terminal of an LRU, and then you have the subsystem of the LRU, and we'll see that in a drawing to understand it just a little bit better. But whenever you hear, in the strict sense of the word, a 1553 terminal, or the bus controller terminal, the remote terminal, in the strict sense of the word, it's just the 1553 part of the unit, but it's just become now that everybody uses whatever the LRU is that's doing the bus controller. They just call that the bus controller. There's only one bus controller at a time.
Hi, Melvin.
Yes.
Yes. It's Joe. Hi. Yes. I signed out the form, so I'll just leave it on my cubicle, in 04B242. Okay, sure. I'll come over and pick it up. Okay, great. Thank you. Thanks, Joe. Okay, bye-bye.
Okay. Hey, it'd be great that if you're not talking, that you mute your mic, so that if you have another conversation, that it doesn't echo back around through. One of the bus controller, so you have one bus controller at a time. You can set up backup bus controllers. There are different ways to enable them. The Air Force said under Notice 2 that you would not have a software-controlled backup bus controller, but a lot of people will implement a secondary line. It could be as easy as a discrete that gets dropped out that kicks in the new bus controller. A lot of people will have a serial line going between the two potential, the bus controller and the backup bus controller, and just pass a simple message. That way, because sometimes an LRU can be up and operational, yet not being able to send a message, where that if you just have a discrete line, it could be holding the line up, but it in essence isn't working. Remote terminals. Go ahead. Yes, please.
What is an LRU?
Line replaceable unit. I'm sorry, that probably doesn't apply much to satellites, but when on an aircraft, which is where 1550 originally started, if you had a function like a nav unit, it would be called an LRU because the repair guys could replace it right there in the hangar. So a line replaceable, they could pull it out and put a new one in, and so it became slang that's just used throughout the industry for a box that would sit on the 1553 data bus. My apologies for using that for here.
Oh, no problem. Thank you.
Yeah, thanks for asking. If I use a slang, please call me on it. Again, the remote terminals. You can set up a remote terminal as a backup bus controller, but remote terminals are never bus controllers as a whole. I have seen people take that and make it a bus controller. I wouldn't advise it. What I really recommend is that you'd have a monitor that is your backup bus controller, because monitors listen to everything, and then you'd be able to keep up on all the data and in operations that are occurring on. Where a terminal may not be quite so bright. Up to 31 terminals allowed on 1553 currently. Let's see here. Bus monitors. Bus monitors listen. They never transmit. If it transmits, it's no longer a bus monitor. Abaco has two different kinds of bus monitors too. They'll have one that follows the strict sense here that connects in directly into the data bus on a coupler, and then they have one that's a high impedance. And high impedance monitors can be really nice because they don't affect the bus, the impedance on the bus. And I've been on a number of strangely installed 1553 data buses that if you connected anything on them, it would go down. So a passive one can be very nice. I mean, absolutely a high impedance one. So anyhow, again, monitors do nothing but listen. Any questions? All right, so this is a bus layout. When we refer to 1553 and we call it a data bus, it has really become to be understood that it's a dual redundant set of wiring, if you will. So you would have the A bus and the B bus, and that would be, you know, one channel with A and B sides. And if you had another complete different system, that could be another channel. So you've got your bus A and your bus B. There are some implementations where people use only one. They only implement with one. I don't recommend it. I think one of the newer notices actually calls you out and says that you can't do that if you're doing a military, you know, type installation. But there is things here also to consider too. I know some of the original shuttle buses were actually quad, you know, buses, and so it's kind of interesting the way that the early times were put together. The transmission of information on them can be they can be alternated. Early designs, they used to transmit the message on both A and B bus. If you're in something that requires even more high integrity, you might look at that. But 1553, with the ability of the terminals to see the message and then to respond back that it got it, typically it doesn't need that, but it's a consideration. Here also that we don't show it here, but you'll see them later on. As the RTs and the bus controller boxes are coming down and connecting into to bus A and bus B, this is a coupler. And there's historically two different ways of coupling to this wire, but the method that's used now is through what's called a transformer coupling, and so that's it keeps the common mode problems out of the way. Let's see here. So that gives you, one thing we don't have here is that every bus ends in a terminator, 78 ohm terminator. So basically what you're doing is you're putting together a transmission line. And so if you haven't caught on, what we're doing at first is we're going over the physical aspects of the data bus, and we'll move on from there in just a bit. Any questions regarding this general layout? Awesome. Here's another example of a typical 1553 system. And so it isn't much different than the other picture, but just throwing that the difference of the terminal actually being separate from the subsystem. So if you are reading the guide that I sent out, or the standard, you'll see it talk about subsystem, you're talking about terminal. Well, like here, the whole nav unit is considered the subsystem, while RT would be the terminal. Mission computer would be the subsystem. The bus controller would be the terminal, the bus controller terminal. And I just wanted to touch base on that to kind of get that picture in your mind. So in this case, with our products, this would actually be your card. Your interface card would be considered this part of your system. Remote terminals. Remote terminals are kind of interesting designs. So remember that when 1553 was first designed, it was back about 50 years ago. And in that part of the design, RAM was expensive, you know, and so you very much limited the amount of RAM you had. And so what they would do is that they would create subaddresses. And these subaddresses would be 32 words of storage area. And you would have 30 subaddresses in an LRU. Actually, you would have 60, because you would have 30 that would be on the transmit side of the buffers, and you would have 30 then on the receive side of the buffers, you know, for a terminal. And then it would you would specify how many of those words for the message that you would use, and it always would start at the first word slot and count out. So if you specified 5 words, then it'd be the first 1, 2, 3, 4, 5 words. If you specified you know, 20, then it would be the first 20. Strangely enough, in the actual 1553 word, if you would specify 0, all zeros for the number of words you want, you actually got 32. So that's just a little bit of thing that people have a problem getting straight in their minds. So just a little bit of introduction here to the architecture of the remote terminal. As I mentioned before, there's bus coupling. There were actually originally two types of bus coupling, one called direct couple and one called transformer couple. Early aircraft like the F-15 would have the RT just tied directly in to the data bus lines. In fact, what would really happen is that like bus A would come back and actually the bus would go inside the system, and then it would then have these wires here connect to it, and then it would leave again and it continue the bus, because a direct couple bus can only be a maximum of 1 foot long, and you can waste that inside the LRU, inside the system very easily. So nowadays, because of that problem with interrupting the bus, and also with the distance of only 1 foot, the transformer coupling is really much better. It's also a mandate. So what you have is that you have the transformer coupling here that's in the coupler as it attaches in to the resistor, isolation resistors to the data bus. And those lines from your computer, from the computer board, can be 20 feet maximum. Any questions? There are some weird things that do happen. There are people who have implemented, I've seen 70 and 80 foot stubs, and that was very interesting. You definitely want to be very, 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 very careful when you violate the spec on what you're doing on the rest of the bus. That bus, if you tied anything in on any of the couplers, it would die. You could have one coupler for that LRU and one for the bus controller, and that was it. I've seen the data buses, by the way. The standard in when it first came out defined that the data bus could be as long as 300 feet. And then in the B version, they took that out. And part of the reason for that is that you can actually go longer. I have had over 1,000 foot data buses. And again, when you go far, you just got to be careful that you're going to affect the amplitude of your signals and your response times. And so it's those are just things to keep in mind.
Hello?
Right. Yes.
Oh, I didn't know if you could hear me or not. Another reason they got away from direct coupling is that if you have a short on your bus within an RT, you bring down the entire bus. With transformer coupling, that goes away. Very
true. Yeah, excellent. Yes. Yeah. And so that's really cool. And of course, the whole thing with the common mode rejection. That's pretty cool too. Thank you so much for adding that. I appreciate it.
You're welcome.
The bus couplers. So this here on the right is a 2-stub coupler. This would be the data bus coming through this way. And you can easily take this and connect it to a 1553 data bus wire and take it further out and have more couplers. What a lot of people will do in the lab is that they'll buy the size coupler. Maybe it's a 2-stub, maybe it's a 4-stub. I've seen people buy, I don't know, 12 or 16 stubs, just crazy stuff. And you can actually make that your data bus. You can take this terminator here and put one right there, and then take another one and put it right over here on the right side. And this now becomes a tiny 1553 bus. So it could be like your A side, and it would support 2 terminals, maybe a bus controller and your single RT, if that's all you've got on there. It makes it very easy for setting up your system. If that's all you've got and you're on a bench, there's no need to have actually data bus wire, except for, of course, the stub wire coming off of here. For our boards, you would need that wire to connect from here to the harness cable coming off the card. As mentioned before, I kind of stole this picture from this point. Go ahead.
I have a question. What kind of coupler is that you were showing? Is that a direct coupler?
Are you asking who made it?
No. What kind of a coupler is that? A direct coupler or a transformer coupler?
Oh, yes, this is a transformer coupler. Yeah, thanks for asking that. Yeah, it's pretty rare, really, to find, at least most places that I've hung around, I had to special order if I wanted to have a coupler that is made direct. That this has the transformer inside and the isolation resistors, and so this is made for transformer coupling. Is that good?
Thank you.
Thank you. Okay, so in this diagram here, I wanted to show what it would look like if you had decided to make the coupler your bus. And what would you need? If you said I had one channel 1553 card and I wanted to connect up my network, what is the smallest I could do? Well, you'd have to have two sets of these. So you'd have to have this set and you'd have to have this set. And so this could be your A bus and could be your B bus. I mean, they're identical. So there's no weirdness in it between the two. It's just that if to make your dual redundancy, you get your A channel and your B channel. And this is the hardware you'd need. You'd need this coupler, and then the two terminators and the two RT lines. And by the way, data bus lines and RT drop lines or just terminal drop lines are the same. So there's nothing special about them. If you have one, you have the other.
Hey, Bill?
Yes.
If you were going to truly go with this small a setup, what would you have any issues of just using one 6-foot cable between the bus control and the RT and then setting the software to do a direct connect? Do you see any issues with doing that? If you're really going to just have 2 units on the bus?
Okay, so we have 2 units.
You're probably not testing as it'll fly. I'll give you that, but.
Right, and you're talking about getting the 2 to communicate or what?
Yeah. It's like, I mean, even the unit I'm currently working on, the test set, it's a space vehicle simulator, and I'm the bus controller, but I only have one RT out there at the other end. Now, we've got some long links to make, so we are using, the stubs and all. But let's say that your unit was going to be sitting right next to your test computer, and you only had 2 connections. And I know within your software, you can go and set it for direct connect when you're doing the bus setup. Do you see issues with doing that for someone if they didn't want to have to purchase the additional terminators, stubs, and everything? Or do you just say it's not a good idea?
Yeah. Well, I guess in general, I find that's not a good idea. When I used to play with this stuff a lot back in the labs, I would make sure that I never had 2 terminals closer than 1 foot to each other outside of this coupler box here. But that was just my rule of thumb. I mean, you could do it direct, but I just wouldn't.
Okay. Yeah, this is Bill Tilman, and I definitely do not want to see anybody do that. You really don't want to do that because really when you connect to a bus coupler, you have in the first order, you've got a voltage divider. When you go through the bus coupler, there are a couple of series resistors before it touches the backplane or the bus cables, and then a couple of series resistors again. So coming on the input to a device that might be right next to you, it's at approximately 1/3 the amplitude as opposed to the full amplitude. I have seen transceivers get burned out because of because of some bounce that was seen on the wire. It was a lot worse of a connection than just a direct connection. So really the terminators help take that ripple out of the top of the waveform. And also it knocks it down by 1/3 of the voltage. Also, you're dealing with, a lot of times in the lab, you're dealing with single unit resource that you have across the company or first unit devices. So very few or very expensive systems. So you're taking a chance at possibly blowing out that front end. It really does not happen very often, but I have seen some people spend a lot of time waiting for parts to be repaired. So.
Good advice. Thank you.
Very cool. Yes, thanks for stepping in there, Bill.
Yep.
One other thing that may be fun here is looking at what the data bus would look like on a scope. And so as you would look at the signal, this is a really clean signal. You see it's a Manchester waveform, and it has a sync here at the beginning, and then ends in an odd parity. I think the thing that can be interesting with these, and of course this scope is looking at you've got a distance between the two terminals, and one's close by and the other one's farther away. Let me see some of the fun things with this. It won't look this nice on most. If you're working on an aircraft, it's pretty rare that you'll see it look this nice on an aircraft or an older bus. You'll see a lot of tail off, a lot of jaggedness there. The waveform's not near this pretty. It will be jagged and could come down like that, and it's just it'll get kind of messy. But it's good to know what a gold waveform looks like, and then also you can see when you have something really going bad. Abaco does have a product, a bus monitor that does have a waveform out connection, for a no scope. So that's kind of cool. I just thought we just kind of throw this one out here. If anybody wants to do a deep dive on this, we can do that another time. Transmission details. Okay, so it's one megabit rate effectively. The word sizes are 20 bit times because you've got the sync times at the beginning. Only 16 data bits, and then plus the parity. And so that it makes up the total 20 microseconds time frame for each one of the words. Word formats, there's 3 kinds. There's a command word, there's the data word, there's the status word, and that's it. Message-oriented transmissions, so it's when a 1553 analyzers also look at it, they look at it on a message base. So it'll flag a bad message. And it might flag multiple parts in the message, but it's flagging it based on a message level. And so when looking at that, it is the message block and not the word. Okay, we'll go further now and see what that looks like. Okay, so word formats. Again, you heard me refer to bit times, and so this is bit times on the bus, on a 1 megabit bus, and you have your sync that for the command word is up for 1.5 bit times, and then it crosses 0, and then it's down 1.5, and that's what all of the timers in the terminals are looking for. And so once it finds that, then it knows that it can sync and start reading the rest of the word. And that's basically then how the word's decoded now that you've got the time encoded in with the word itself. The next 5 bits are the remote terminal address. Every remote terminal has an address. Most of the time, in many cases, the address is hardwired from an external port on the system itself. Other times it's software defined. And so that way you can change it on the fly if you need to. Most systems, once they're in place, though, that's what they are. They're not going to be changing unless, of course, you're adding stuff and you need to change things around. So you have a 5-bit terminal address. You have transmit receive. Remember, in the olden days, this would tell it which set of buffers that it would be dealing with, transmit buffers or receive buffers, SubAddress and mode codes. And so this defines the SubAddress. Mode codes we'll get to in just a little bit. So which SubAddress and then how many data words are you looking at? Again, if these are all ones, if it's all zeros, it's 32 data words. All ones are 31. Parity is odd. It's always odd. Now, only bus controllers have command words, and that's used a little bit lightly because there is a special case where the RT will send out a command word effectively, and that's into the RT transfer. But that was initiated by the bus controller telling one RT to send information directly to another RT. And so then again, that was still initiated by the bus controller. Data words can be by both. A bus controller and an RT can both have data words. And so the data words have their own sync. It's an upside down sync compared to the command word. And then 16 bits of data. And so for the most part, you can arrange them in the direction that you want. However, there is a notice that that does specify what direction they'd like to see it. And then parity is odd. Status words are only sent by the remote terminal. Bus controllers never send status words. Monitors don't send status words. The status word has the same sync as the bus controller does, and it would use this instrumentation bit here to differentiate itself in early designs. That would have a consequence that it would also reduce the number of subaddresses that you could have. And so they got away from that pretty quickly once monitors became smart enough to be able to differentiate between command words and status words. So it's basically not used anymore. In a status word, so if a bus controller sends a message out to the RT will respond if the message is valid. That means if it pertains to its RT address, and it has an option to respond or not respond if it's illegal. And most systems nowadays will respond to an illegal command word, and we'll get into those definitions in a little bit later. And we'll get into the details of what these are: message error, instrumentation, service request, the null void area. That it's very rarely is the people violate the standard and use that area. I've seen it done, but it's very rare. A broadcast command received, the system's busy, subsystem flag, dynamic bus controller, a bus controller acceptance. This is where you can pass the flag of being the bus controller. Remember, you can't do that by just software anymore. And then you have the terminal flag. And we'll get into those meanings a bit more. Any questions right here?
I have a quick question.
Sure.
The word coming from the remote terminal address or remote terminal shouldn't, for example, the data word, there's no address to indicate the bus controller. So how does it find its way to the bus controller?
Very good. So these are all set up in messages, and what happens is, and you'll see that in just a minute. So you're good lead in actually, is that data words always follow contiguously after a bus control message if the RT is to receive data. If the RT is to transmit data, then the status word goes out, and then right on its hiney right here is the beginning of the data words, and they'll be contiguous. And so that's how you know that the data word belongs to what message interaction.
All right, Roger. Thank you.
Okay, and we'll see that here in a layout that I've got in just a little bit. Command word, closer look at the command word. As we talked about before, it's got 5 bits for the RT address, the transmit receive bit, SubAddress, and then word count. And setting these up like this, this is how they would be translated. And then if you are looking at for a hex representation, which you can see on most of the data monitors, that's what it would appear to be. Parity is not seen. It's part of the hidden part of the words. And that's just kind of an easy sample of decoding what you might be looking at. Okay, the data word. And it's just that. It's 16 data bits. And if you're you can look at a data word in a decimal value. You can look at a data word in the hex value. A lot of people, as they get used to seeing what data should be related to what kind of message and what subaddress, they're just reading hex all the time. In the bus tools monitoring package there for analysis, you can actually have all kinds of engineering unit conversions and even some displays that you can set up, actually quite a few displays that you could set up for the data so that you don't have to be decoding binary or decoding hex or decimal values. But if you wanted to, you could do it too. RT generated status words. Okay, so the bus controller sends out a message telling the RT to receive certain data words that it is sending it. The RT would receive that entire message. It would validate the message, meaning that it follows the proper form and it belonged to it. And then it would respond within the 4, if you're looking at it from the bus controller's point of view, 14 microsecond time frame, with the status word. And if everything's good, then basically it's this and the rest of it's empty. If it's not, then it will flag what are the different problems that you have here. And we haven't got to the part yet where we've defined illegal words, but if a bus controller were to talk to an RT and tell it a certain subaddress or data word or subaddress data word combination that it doesn't support, that could be, that's an illegal command. The spacing between the command word and the data words is an illegal command. So these things would flag a message error bit, and telling the bus controller, hey, there's something wrong with what you're trying to ask me. There's an instrumentation bit, and we've talked about that, and it's just basically not used anymore. The service request bit, this is an interesting bit. It's used to signal the bus controller that a terminal needs service. Now, typically in 1553 land, the bus controller is defined all its messages that it's going to ask. So it knows what to ask. It's kind of like, where on an Ethernet switch, you would define who gets to talk to who and what would happen there. But here it's all done within the bus controller. And if something odd were to come up with the remote terminal, and it needs to be asked a question that's outside of the routine, what would be called a bus list, then the bus controller would see that, and it had to be predefined within the structure of the data bus, what the bus controller would do if that particular terminal came back with a service request bit set, and then it would ask it questions, and that can also be done through mode code questioning, and And it can be a rather neat way of implementing ad hoc questions into the bus controller. Broadcast command a receive bit, and of course we just talked about exactly what that is that hey, I received it. It's used to indicate the previous valid command received was a broadcast command. And so this is when there's a message we haven't talked about here, but when the terminal is set to all ones, it can bus controller can transmit out to it's basically a separate terminal address where the RT, if it's set up this way, can listen to any RT can listen to that message, and none of them ever respond, but they put in their status word that they received it, and that's what that one would be right here. And then the next time a message would come through, it would be erased. And it's just a good way of keeping track of, hey, I'm allowed to see a broadcast message, and I received that broadcast message, and this is where I'm going to store it until you talk to me again. Busy bit, it's used to indicate that the terminal is busy. And so in certain situations, it's really bad form to use the busy bit. Most of the time, the busy bit's used when the system is coming up and it's not fully operational yet. It'd be very strange to implement that during a time that that the system is supposed to be fully operational, and many people frown upon it. Subsystem flag bit used to indicate that a terminal has experienced a fault condition and that the data may be invalid, and it's just that. You know, I've got data for you, but it may not be accurate. I'm having trouble. I'm experiencing difficulty. It might be also a situation where you might have sensors that have gone bad and or they're questionable. You know, that's just different ideas. Dynamic bus control acceptance bit. This is used to indicate the acceptance of a dynamic bus control offer. So under what's called the mode code operations, you can send that message to, out, and it can then show an acceptance of bus controller acceptance, and then the other one's supposed to turn off and or go do something else. Terminal flag bit. Used to indicate that the terminal has experienced a fault. So this is more like a hardline thing, like I'm no longer working right. And so it could be a progression, right? You could start with a subsystem flag bit, and then you could end up here. Again, terminal in the strict sense of the word would be the RT or the BC part, but it's used more generally now. Message types. Any questions to this point?
Yeah. Hey, Bill. Mo had a question in the chat box.
Okay, Mo. Let's see if I can bring the chat box up.
Here, I'll read it to you. It says, that is the BC_control M frame and question mark. If so, NGP definitely plans to add it to the legacy design. It should neatly complement the BC trigger repetitive mode.
Right. Yes. I'm sorry. I've lost some things here. Just a moment.
That was not about it. That was something that Bill Tilman and I were discussing. It should have been offline. I fired it to the group. So sorry about that.
Okay.
Yeah.
All right. Yeah. We can take it later.
This is Bill ambiguity, but yeah. So this is something that you weren't discussing initially. So yeah. So that was user.
Okay, that's fine. I can't. For some reason, I can't pull my chat up, so it's a little frustrating. All right, message types, guys. Okay, so this one thing that is noted here at the bottom is the optional broadcast. So you have the bus controller sending messages to the RT. So it's telling the RT, hey, you're receiving data. You have the bus controller telling the RT to send data to the bus controller. So this isn't initiation. This is what the operation of data transfer is actually looking at when you see this order. And then you have the RT to RT. And so this is always started by the BC telling one RT, go, send, typically it's sending data to another RT. And then mode code commands. There are a certain number of these commands that can be broadcast. That's kind of interesting from that point of view, I guess. Some of the newer notices frown on the use of broadcast, and they've pulled it out to the side in their systems. But it used to be used a lot for transmitting time out to everybody, or a sync. There are some big aircraft that carry some interesting stores on it, and they actually use that sets of commands on a broadcast to tell the entire subsystems to swap over entire memory banks and actually become a different kind of subsystem for a fractional period of time. And so it's kind of a neat way, an ingenious way actually of using that type of command. And my computer froze. There we go. All right, so other terminology for 1553. Drawings are worth 1,000 words when it comes to 1553, but let me throw these words at you and then we'll take a look at the drawings. Intermessage gap. This is the message time of no less than 4 microseconds. It's the gap between the bus controller between its messages. And so it can be no shorter than 4 microseconds. That's measured from the zero crossing of the parity and the zero crossing of the sync bits. And so that's pretty tight. And then of course you can have your messages strung out as far apart as you want. But that's basically the closest they can become. So intermessage gap time is the time between messages. Response time. This, of course, is like if you're sending the message to the RT and it's going to send back a status word. It's got to send it back 12 microseconds at the most after it received it, because it means that on a long bus that the bus controller is going to see it at 14 microseconds. And so a lot of people, in order to keep their buses snappy, will set them up at 6 microsecond response times. And just keep in mind that the bus length does have something to do with the total time. There is capabilities on the Abaco cards to violate these, have longer times, and of course the minimum is 4 microseconds, and it's not wise to get any lower than that because you'll create errors on the bus. No response timeout. All right, so if a message goes out and the response doesn't come back, that timeout occurs at the 14 microsecond. That's why you have 14 microseconds for that first part of your RT's response to come back to the bus controller, or it will declare it a timeout, and it gets messy sometimes after that. And of course, it's a half duplex bus. I guess I should have mentioned that just a little bit earlier, but you probably caught on to that since the bus controller is initiating all of the communications, the communication message goes across, responses come back. Don't have multiple messages, like you wouldn't send messages on the A bus and on the B bus and be expecting everybody to be responding to it. That actually would be called a superseding command. And it can be done. And sometimes people use it as a recovery methodology. But 1553 is a half duplex. what does that look like? So this drawing will help us out just a little bit. You know, again, a picture is worth 1,000 words. And with 1553 and looking at message packets, so if this is a BC to RT, that means that the BC is sending data to the RT. And so what first goes out on the line is a receive command to an RT, again, with that RT address in it. And then you have the data that the bus controller wants the RT to receive. And notice that it's contiguous. There's no spacing between these blocks. And it moves from the parity right into the data word sync. And then you've got this time period here, which is your response time, and then your status word. Remember, this is a response time, meaning that the RT has got to respond within that 12 microseconds. And then here is your intermessage gap time, and that can be as long as you want it to be, as long as it's necessary for your bus to operate properly, or maybe you just don't, it's not that busy of a bus. And then the next command word would begin here. Similarly, if you're coming out with an RT to BC message, then the bus controller sends a transmit command to the remote terminal. And then it will start with a status word and then have the data contiguous on the end of it. If you just had a status word message, an RT message coming back, and a bus controller message on the bus, and you didn't have any perspective to it, you wouldn't know the difference. It could become really messy. Again, if they're just thrown out onto the bus. So you've got the status word, contiguous data, and that's the end of the message. And then the next one would come. Now this is one that's fun and a little tricky. This is an RT to RT transfer. And so this is where you're telling one RT to send data to another RT. And so the receive command, the bus controller sends out a receive command, and on its tail, it sends out a transmit command. So then the status word is then responded back from the RT along with data words that goes out. And then the second RT receiving the data would have its status word response. And so it can get a little confusing, but there is a requirement that that all terminals be able to understand that and not flip out on it. And then here we have mode codes without data words. A mode code, so telling the terminal turn off the A bus or turn off the B bus or sync, and we'll go over a list of these. And then if it's sent directly to an RT, then the RT will respond with the status word and the next command. If the mode code has data associated with it, then it's only one data word. So this is where the mode code command requires a data word to be sent back. And if you ever get involved in setting up an RT vector interrupt, that does include a status word and mode code response with a data word, and that can be really cool to set those up. Again, we'll cover that on another session. A bus controller with a BC data, so we've got the mode code and a data word. And unlike the early specifications in 1553A, they didn't specify how many data words could be associated with the mode code. And sometimes you would see up to full packets of data word messages being associated with mode codes. I think the biggest one I ever saw was on an early implementation. They actually had 19 data words associated with the mode code. But of course now it's defined very clearly as being one data word. Any questions? Awesome. Mode codes. Okay, so in general, mode codes are used to manage the data bus hardware itself. Implementation of mode codes is optional, except that that was There are some notices that bring it into focus that you've got to implement certain types of mode codes now, but for the most part, they're optional. And so then when 1553 is used in its full robust mode, there's 15 mode commands, and 9 of which require no data words, and 6 require the transmission of a single data word. Okay, so that's just kind of compartmentalizing all of that for us. Use of mode codes which are not implemented result in illegal command responses. And then the use of reserved mode codes result in illegal command response. And so just a quick entry there of mode codes. So in the command word, you'd have the remote terminal, you'd have still with the TR, and then you'd have a subaddress. And so the subaddress defines when a mode code is implemented instead of a standard message. And so the subaddress field would have to be full of all zeros or all ones. And that was a really early implementation differential. The Navy implemented it one way at first, then the Air Force implemented it another way at first, and it was just too messy to back it out one way or the other. So they both agreed that, well, we'll just make 0 and 31 the mode code location, and then the mode code itself, which is telling the systems what to do. Any questions right now? Mode code examples. Transmit your last status word. So the RT would transmit the status word, and then you'd initiate self-test. There's transmitter shutdowns that affects one over the other, override the transmitter shutdown. I mean, this is set up basically for the most part, just a dual redundant bus. But with data words, you can affect the others. Transmit vector word. That means basically that inside that vector word is what to ask the RT when it wants to interrupt it and be serviced. Synchronize with data. Transmit last command. To transmit a built-in test word. I mean, this is what would happen here on the bomber, but it would synchronize with data, and so it would use this message right here to cause the LRU data transmissions for everybody to swap their buffers and effectively become something else for a short period of time. Close look at mode codes. This is just about the decoding of them, and you know, you initiate a self-test. What it would look like, code-wise. You've got your RT address, and then as its transmitter receive, message, and then mode code. We're calling on mode codes. We got all zeros in the subaddress, and the mode code itself is 11. You're looking at the hexadecimal representation for CO3. Of course, decimal. There's no decimal meaning, and of course, the binary is always there. And so just when you're thinking about mode codes, this isn't a real, aha moment, but just when you're looking at, that's what the type of things you'll be seeing with a command word. Broadcast commands. This uses the RT address 31. It is optional for a remote terminal to be set up to receive broadcast commands. If you want that to happen, you have to go into your remote terminal and actually set it up to do that. You can broadcast mode codes. You can broadcast data words. There's no RT status response. Only the storage of that one bit for the RT saying that it received the broadcast command. Again, broadcast command occurs on just one bus at a time, whichever one's called out. And I guess you could implement it on a bus A and then a bus B. When we're talking about this, as people are using, bus A's and bus B's, there's a number of different ways. The design standards, most of the time people say that you should have at least a portion of your standard messages going over your redundant bus so that you can make sure that everything is operational in case you have to switch all your messages over there. And so that's typically what most do, again, for people who have a need to make sure that the data is even more robust. You could transmit it on A and then transmit it on B, but that's a design decision. I have seen people who have set up their buses and always transmitted on A, and you'd never find any data on B, and that's typically not a good practice. Broadcast commands, just a little bit more about them in the mode codes. It all goes out as a subaddress 0 or 31, and then the mode code to be included and what that would look like. And as again, this is one of those things just to get you used to seeing what it would look like to see a broadcast command go out with mode codes. And of course, it's a receive. Broadcast commands always receive. Let's see here. Not sure this is going to give us any better clarity on anything. Jump by it. You've heard the terminology when I refer to illegal versus invalid. Illegal means it just doesn't work. It doesn't belong on the bus. There's something strategically wrong with the form of the waveform, typically, or the RT address. Valid words require that the sync must begin. That each word must begin with the valid sync. So it's got to be 1.5 times up, 1.5 times low, or vice versa for data words. Each word must have valid Manchester 2 encoding. So if there's a violation in the bit as it's crossing, then that would be invalid. Each word must contain 16 bits and 1 parity, and the parity must be odd. So if there's any violations here, it's invalid, and basically nobody on the bus should be responding anything to that. It should be a total no response. It should be just received like there's nothing there at all. Remote terminals were considered commands valid. So in RT, if it is a RT address that it's been told to interpret, then it's valid. If it's not part of its RT, I've seen multiple RTs as people are consolidating systems. I've seen multiple RTs end up in a system, but most of the time it's just one, and the system just sees that one RT address, and that's what it codes on. Rote terminals were considered message legal. Given the following, that the word received passes a validity test, so it's got to be valid. Continuous words are maintained in the message, so there's no gap between data words or either between that and the command word or the status word or the data words individually. And of course, that the address, subaddress, word count, and TR bit combinations are implemented within the RT. And so if it's illegal, it means that the subaddress, word count combination, transmit receive combinations are not supported. Illegal versus invalid. Illegal commands result in a message error bit being set in the RT status word. Invalid commands are not responded to. So I had a discussion about this earlier, where if it's illegal, the message error bit in the status word gets set, and the RT responds with that. And that's basically it. As you can see, I stole this from Bill.